Welcome to my presentation on propeller perfection, optimization using JMP for efficient experimentation. My name is Brian Scott. I am a systems engineer intern at JMP Statistical Discovery. Just move that over. All right. So why do we need a perfect propeller? Why is this relevant to us? All right. So this graph over here demonstrates just how the eVTOL market is increasing, almost exponentially. Currently, we are, right here, 2025, but if you can kind of see the way that we're growing, the need for propellers is pretty evident. Now, why do we need efficient propellers? So this graph over here kind of just explains to you, the need for power throughout a typical mission profile of an eVTOL aircraft, or just any VTOL aircraft for that matter. So these two red bars, you might be asking, well, what are those? That is takeoff and land. So that's where the aircraft takes off and lands vertically, and it 100% relies on the propellers to lift the entire weight of the aircraft for takeoff and then achieve a hover and descend for landing. So you can see that we really need a lot of power during these two times of flight. And over here, we can kind of see, this is how the battery voltage drops as we go throughout the mission profile. And again, you can see the two red bars for takeoff and land. All right. So who is this relevant to? Here's some of the key players in the eVTOL industry, and Archer Aviation, I would say, is probably at the forefront of this. So you might be asking, well, why do we need efficient, propellers? Well, as you can see, the Archer aircraft over here has 12 propellers. Right, all 12 of them are used for takeoff and landing, and that's really where that high power draw is coming in, using all 12 propellers to take off and land. And then during forward flight, these front 6 actually rotate forwards and the back 6 turn off. So not as important there, but really in takeoff and land, you've got all 12 propellers lifting the entire aircraft. And here we've got a German company, Volocopter. Theirs is quite a different concept to the Archer, but you can see it's got 14 propellers, and none of these tilt forward. So at all times, all 14 of these are lifting the entire aircraft. And here we've got a local company, Beta Technologies, based out of Raleigh, North Carolina. They have quite a different, concept or kind of design ideology for these in their propellers. But again, as you can see, all 4 of these propellers are used to lift the entire aircraft, and again, when it comes into land. So here's just a snapshot of, where we're going to get to. So referencing the previous graph where we have that really high power draw at the beginning, at the end of a flight mission, what you really need in those times is a lot of thrust. So you can see this red line over here is the propeller that JMP suggested to us after the DOE. And we can see that it has a lot of thrust, but it also has a lot of power, right? So what we need to do, it requires a lot of power. So what we need to do is there's some sort of trade-off, right? I want to maximize thrust but minimize power. So I'm going to have to settle somewhere in the middle. So what we did for this project is we did a DOE where we compared 60 different types of propellers, and using the data from that, JMP was able to spit out, the most efficient propeller, which is this red line. I then went to one of my professors and said, you're an expert in the industry. Using what you tell me what you think the most efficient propeller is. And they came up with this blue line. I then did it myself. After a couple of years of schooling, maybe I can design the most efficient propeller. And what I came up with was this green line. So if I scroll down over here, here's my efficiency curve. And I can see that the red line, the JMP propeller, beats the professor's propeller and my propeller at all stages for efficiency. And this over here is just a picture. We actually 3D printed this propeller, and we're able to test it as well. So here's a physical representation of the actual propeller. Right. So currently, if you were to design a propeller, this is probably what your workflow would look like. You would have some kind of variable range. You would make some kind of assumptions to make your analysis a little bit more simple. You create a data table. You would maybe write some kind of MATLAB function, and then you would do your testing. And since testing like this is quite difficult, you would most likely do something called OFAT testing, which is one factor at a time. And this is what us at JMP, we are trying to eliminate, this OFAT testing. Then you would achieve some kind of result set, and you might go through another round of testing. You would then get to a final product. Now for the analysis, There's a lot of different ways to analyze a propeller. The one that we chose for the purposes of this project is something called blade element theory. So this is just an analytical method to mathematically solve for the thrust and power draw of a propeller. And if you were actually doing this in the real world, you would want to, employ some kind of higher fidelity physics solver, and that would be some kind of CFD package or, just some kind of fluid solver to be able to do this for you. So what are the problems with this? As mentioned before, it's very complex. This kind of analysis is very difficult to do. It's very time consuming. Some of these CFD analysis can take hours, if not days, to run. And it's very computationally expensive. There's quite a high cost associated with this. So what we're trying to do is make a more efficient way that we can do this. So this is the workflow that we're trying to get to. Now, the complexities of the previous workflow, we've eliminated those and we've introduced this purple block over here. Now, if you want to learn more about exactly how we did that and exactly how we combined MATLAB and the JMP scripting language, there'll be another video that you can click on to go and watch a step-by-step instruction set on how to do that. But for the purposes of this video, we're going to move on with the presentation. So what we used is design of experiments. So you might be thinking to yourself, well, what is design of experiments? Imagine you are these two, professors or mad scientists, and you have some kind of output, which is this line, and you have these levers, which are the other inputs. Now, let's say you want this line to be as straight as possible. So you might move, lever number 1 down, and randomly the line goes straight. So you think, okay, well, lever 1 has to be down. But then you move lever 2 up, and now the line is skew again. But you thought, well, if lever 1 is down, the line must be straight, so lever 1 must be down. But there's some interaction going on between lever 1 and 2. Now, if you were able to do OFAT testing, it would be very difficult to get these interactions by doing just one factor at a time. And if you had a lot more than just 5 propellers, it would be impossible to do. So this is where DOE really comes into play. Using a designed experiment, you're able to get information on all of your factors and the interactions of those factors in as few number of runs as possible. And that's what we went ahead and did. So if I open our data table over here, we can see that we have about 6 factors, and we already have our results populated in this. But if I scroll down, you can see that we have 60 runs. And then we have some of our efficient settings appended to the bottom, rows 61. So this is what we're trying to get to, right? So if I go ahead and I fit my model, this is something called the JMP profiler. So this is, your what if settings. What if I change my max chord location to 0.74? Then JMP is going to give me a predicted value for average thrust coefficient of 0.478 and a predicted value for average power coefficient of 0.44. Right? So now what you can do is you can tell JMP, well, I want my average thrust coefficient to be as high as possible, and I want my average power coefficient to be as low as possible, really maximizing my efficiency. So you can tell JMP to do that, and then you can go ahead and you can click maximize desirability. And then JMP will go ahead and it'll change all those settings for you. And there'll be a trade-off because you'll need to maximize thrust and you'll need to minimize power. And you will then be able to get the optimal combination of those two settings. And in order to achieve those settings listed in red on the left, you will need to change your variables to these numbers at the bottom here, which are your most efficient settings. Now, what do these gray bars mean, and what do all these, squiggly lines mean? So the gray bars are the error bars. So you want those to be as tight as possible. So in this case, we've got pretty good error bars. And the squiggly lines are just telling me how my variables react with each other. So again, like I mentioned earlier, this is my what if playground. So if I move these, you can see how everything else is adapting to the change that I've made. And the fact that the shape and the curve of those other lines is changing is telling me that I have some kind of interaction between factors. And I can change any of them. What if for some reason I knew that my number of blades had to be at 3, right? I could just put that at 3. And I knew that my tip pitch had to be, at 15. I could just change that. And then JMP will automatically update the other settings, and it'll tell me, what I need to set everything to in order to achieve the best results possible. All right. So just to reiterate some of the conclusions we were able to achieve using the DOE and using our new integrated JMP workflow you can see that at every point along my efficiency curve, this red line is outperforming the professor's blue line and my green line, meaning we did a good job. We have an efficient propeller at every step of the way. Now, a very common analysis tool used in the aerospace industry, particularly for propellers as well, is something called figure of merit, right over here. So we can see that our figure of merit, the red line, is above the blue and green line, again, every step of the way, which essentially is just telling us you've designed a good propeller and you've designed an efficient propeller. So I showed a picture earlier of the 3D printed propeller, and what we're able to do is show you just a quick simulation of what it looks like as it goes through every layer within the 3D printer. And if you wanted to learn more about 3D printing, JMP has a video about that as well. And we're able to also follow the extruder toolpath as it prints every layer of our propeller. So you can see it starts on the outside, just filling everything in, and now it'll outline the entire propeller, and then we'll see it'll fill in as you go along. Right, so you might be asking to yourself, well, this looks great. What next? What do I do? I want to implement this into my workflow. And the next step would be JMP has a 30-day free trial where you can download and you can start accessing all of these DOE tools and many other tools that JMP has to offer. And you can implement all of these into your workflow, whether you are designing propellers or whether you're designing complex manufacturing processes. You can use DOE and you can use JMP to optimize any of your workflows.